Hi class. In this last video on the method of steepest descents in asymptotic expansions, I want to talk about using the method of steepest descent to evaluate the behavior of the Airy function in the opposite regime. Instead of x going to plus infinity, I want to evaluate it for x going to minus infinity. Again, I warn you that sometimes in the literature what I mean by plus infinity and minus infinity is reversed. Sometimes you'll see x going to plus infinity being not being the oscillatory regime which we found. And again, I remind you that in the last video we found there was two stationary points. We had to modify our path to include both. Roughly speaking, here was the path. We needed to include both. This is the form of the Airy function we got for x going to plus infinity. Now, what about x going to minus infinity? It's convenient to deal with a positive parameter that's getting large, so I'm going to write x as minus its absolute value. So the Airy function, which with my convention had this integral form, has this integral representation, can be written then as this expression here, as an integral of this expression, e to the minus I omega absolute x plus omega cubed over 3. If I compute the stationary points of that function in the exponent, I again find omega is equal to plus or minus I in this case plus or minus I, it's along the imaginary axis, of the square root of the absolute value of x. So this is again an example of a movable saddle point. It depends on the value of x we're interested in. We do a change of variables to eliminate that movability. And once we do that, the expression for the Airy function that we want to evaluate here as x goes to minus infinity, x goes to minus infinity is here, the absolute value of x to the 1/2 over 2 pi, times this expansion, this integral here where the absolute value of x is now raised to the 3/2 power and is getting large, and it multiplies this, for the way I've written it here, omega tilde, for this real value of omega tilde where we've integrated from minus infinity to infinity. We now want to analytically continue to the complex omega tilde plane. We do what we did last time. We look at the value of this function, u plus iv. At the critical points in omega tilde are plus or minus I. At plus I, f has the value plus 2/3. At minus I, it has the value minus 2/3. The first derivative vanishes because that's the condition for a critical point. The second derivative is minus 2i omega tilde, just like similar to what we had before. So omega tilde is plus I in this case, and the second derivative is omega tilde. The second derivative is plus 2 at omega tilde equals plus I, and minus 2 at omega tilde equals minus I. If we now consider the value of the expansion around plus I, f of omega tilde, it's the value at plus I plus 1/2, the second derivative times omega tilde minus 1 minus I squared. If we think about going through the saddle in the phi direction, the real part of f of phi is just 2/3 plus s squared cosine 2 phi, because the second derivative is real, so theta is equal to 0 in this case. So the steepest descent path has 2 phi equals plus or minus pi, or phi equals plus or minus pi over 2. I've started to draw this diagram on the right, but let me first talk about what happens around minus I. Here's the value of the function, and the value of the second derivative is opposite what we had before. So if we think about going in the phi direction around the saddle point at minus I, the real part of f of omega is minus 2/3 minus s squared cosine of 2 phi. So cosine of 2 phi has to be either 0 or pi, or phi has to be 0 or pi. So if we look at what this means in the complex plane, here's the saddle point at plus I, here's the saddle point at minus I. The steepest descent direction around the saddle point at plus I is in it's vertical, either the plus pi over 2 or the minus pi over 2 direction. The saddle point at minus I, the steepest descent direction is ascent and descent direction are in the 0 or pi direction, so horizontal. Now, note that the contour that we started with, the contour C, went along the real axis. Let me think about how I could modify this contour. Suppose I wanted to try to modify this contour to try, if I could, let me change to a different color. Let's try a different color even than that. How about pink? Suppose I try to go up through the contour to the critical point in the plus I direction. If I do that, when I come out here, I end up at the opposite side of the ridge that I've over here. And if I try to come back, I'd have to somehow figure out how to evaluate the integral over that ridge. But that's going to be at least as large as the critical point that I have here. So there's no way that I can evaluate that integral going over the critical point at plus I. On the other hand, it's perfectly consistent to modify the integral as I've shown here to go through the critical point at minus I and then come back out. Here I've drawn it as the curve C prime. You can see that C prime starts from the large negative real part in the omega tilde plane, goes over the steepest descent contour or ascent contour at minus I, and ends up in the region we want to be at large positive omega tilde without ever crossing another ridge. So along this path, C prime, we can actually argue correctly that the value of the function is determined by its value around this critical point. Furthermore, I can deform the contour C to the contour C prime without crossing any singularities in the complex plane. I don't have to take this contour C prime. I can think of it as a contour that comes in along the negative axis, comes down through this through the saddle point, and then goes back to where I started. So I don't even have to worry about the portion at infinity if I don't want. But with this contour going through the saddle at negative I can argue correctly that I am the controlling behavior of the asymptotic form comes entirely from this saddle point at minus I. So here we have an example when we're evaluating the asymptotic expansion of the Airy function as x goes to negative infinity of a case where we have two saddle points, but only one saddle point contributes to the integral that we're interested in. So all I need to do is do the steepest descent path around minus I. So here it is. This is the asymptotic expansion as x goes to minus infinity. This is the prefactor that I had before. This is the change of variable to isolate the behavior around minus I. And remember, the direction that I'm going is phi equals 0, which is even simpler. So I just get a ds. And here's an x to the e to the absolute x to the 3/2. Here's the quadratic approximation for the function which multiplies x to the 3/2. So I just get a simple Gaussian integral in the end in the usual way. And here's the form of the Airy function, the asymptotic expansion for the Airy function as x goes to minus infinity. Again, it's overall factor is completely determined, but notice that it's a decaying exponential instead of an oscillatory function. So here is the form of the Airy function both as x goes to plus infinity, it's oscillatory, and as x goes to minus infinity. We actually can get some physical understanding of this. If I think about the differential equation I started with, d squared y by dx squared plus xy equals 0, we'll actually look at asymptotic expansions directly from this differential equation when we talk about the WKB method. But I can rewrite that as a Schrodinger-like equation. I'm going to work in units where h bar is equal h bar is equal to 1 and m is equal to 1/2. So this stage, I can think of this as a time-independent Schrodinger equation. So I write it as minus dy squared by dx squared plus v minus e, where v has the form minus x, so the potential that corresponds to it is minus x, and the energy of the state that I'm considering is actually equal to 0. So if I think about that, here if I plot as a function of x, if I plot the potential, here's the potential, v of x. Oh, sorry. That was backwards. V of x is minus x, so I'll get rid of that. Sorry about that. Here's the potential. If the energy is equal to 0, we see on the left-hand side, this is the forbidden region, where we have the exponentially decaying solution. And on the right-hand side, where x is greater than 0, you see that the energy E equals 0 has a value greater than the potential. This is the allowed region in terms of quantum mechanics. So that's why we have the oscillatory behavior as x goes to plus infinity and the exponentially suppressed behavior as x goes to minus infinity. Now, one of the interesting things here that's illustrated by the Airy function is that if you think about these two expressions, this expression is not the analytic continuation of this. If I think about trying to make x complex and going from the positive x-axis around the complex plane to the negative x-axis, in general, the cosine is going to change. It's going to give me terms that are both increasing and decreasing, but the Airy function has only the terms that are decreasing as x goes to minus infinity. And here we have even a nice physical explanation for why. This is an example of the Stokes phenomena and what we talked about, that in general, when we do these asymptotic expansions, they are only true in some kind of a wedge in the complex plane. So if I'm doing the expansion that's valid as x goes to plus infinity, it's true in some wedge shaped region like this. On the other hand, around x goes to minus infinity, it's a different wedge, and there's no way that I can analytically continue from one region to another. And this is now we can see explicitly when we look at this particular asymptotic expansion, when we look at the asymptotic expansion for the Airy functions, how there are very different forms of the expansion that are not even related by analytic continuation to one another. So this concludes our discussion of the method of steepest descent.